So next week in Dafermos, we talked about the structure of dynamical vacuum black hole spacetimes from stable nucleus.
So I would like to thank the organizers of the conference for inviting me to speak. Particular pleasure speaking with you. So the title of the talk I proposed for hiding the talk is what's written here. This subject belongs entirely to the class general. And what I talk about is work with and so the title is construction of dynamical vacuum black hole spacetimes from Delta Canada. But in some sense, this subject is motivated by one of the major problems in classical phenomena, namely the question of the non-linearity of the Kerr-Boundary black hole surface. So, in fact, I begin this talk with a brief review of how that problem is complex. I wish I could talk about the solution. That problem is too far to be solved. So I will now tell you what it is that you can do, namely this construction dynamic black holes from scattering data. This is almost the opposite problem as possibility curve problem, as we have seen. And then the rest of the talk would be perhaps not standard. I will tell you why stability is so hard and why this problem is actually easy. So most of this talk I will try to convince you that this problem is in fact an easy problem. Now it's not exactly trivial, perhaps that will be apparent, but if I give you the impression that it is, then all the better. So this is the outline of my talk. So let me begin now immediately with a discussion of the stability of Kerr. So here we go. Well, the pleasure, of course, to give this talk to this particular audience because everyone here is, of course, very familiar with the discussion of Kerr-Boundary. So I only give this slide for the purpose of setting the notation, so everyone here knows the two brown Kerr-Boundary solutions that actually apply. So I will know the mass M specific angular momentum as A. Everyone knows that the A0 case is precisely the fortunate case. People might not remember exactly how to imagine it by heart, but in any case, there it is. And the only other numerological fact that I would remind you is that, as we all know, the black hole case is the case of parameters absolute value of A less than equal to R. And the case of equality is the so-called extreme case. So this metric expression describes the black hole spacetime in the case where A is less than equal to R. And the case A is the case of extremality. And of course, if A is bigger than M, then this is something completely different. This describes negatives and numbers. So this is the diagram. This is known to everyone. Also known to everyone is the Dafermos diagram of Kerr. Useful to keep this in mind. Well, because I'm going to talk about dynamics, then it's semantically useful when we say Kerr to always mean something which is globally hyperbolic. So when I say, let's say, the Kerr function, I really mean this globally hyperbolic sub-region of what normally is supposed to be maximally extended as Kerr. So this is a space-time, of course, it's extended for a configuration. So this is a space-time on which it makes sense. So in particular, this space that has a Cauchy surface, the Cauchy surface is sigma, which I depicted here. But in some sense, this So much for curve. And before talking about the role of the curve family in the context of dynamics, maybe I should pay a lip service to the question of its uniqueness as a family of stationary solutions, actually quantum equations. So we certainly believe that the only stationary black hole solutions to the actual quantum equations are the curve family. And this is something which, but it's a theorem under the assumption that the magic is real analytic, to say, developing the magic around n points as a power series. Of course, that's a mathematical assumption which does not have a physical interpretation. We did not talk about causality, because if you can develop everything in power series, then it is such thing as causality. So that's really something which, from the physical point of view, we don't yet understand why these are the only stationary black hole solutions. Nonetheless, one decent progress that has been made recently on this problem is that if you assume that you're given a stationary black hole spacetime which is near the curve family in some precise sense, then yes, you can prove that it is curved without assuming that it is at every point right in matrix conversion to the power series. That's to say, you can show this assuming only the matrix. So this is a very nice result of that. So in particular, that's enough for us here, because that tells you that it makes sense to entertain the notion of the dynamic stability of the curve family, in the sense that if there are no other stationary states near the curve family, and if you believe that perturbing the curve family you will settle down to something stationary, then it can only be a number of the curve family. So it makes sense as a state to entertain the notion of the dynamic stability of this family. But that's precisely the nonlinear stability problem for black holes. So if you want the nonlinear stability conjecture for black holes, maybe I was, no, I can actually write it. Yeah. So namely, this is following. So you remember this Penrose diagram of curve. So think about curve in this locally hyperbolic sense with sigma as a Cauchy hypercenter, so that's current example. So the stability conjecture is as follows. We perturb ever so slightly this current example, so this is some perturbed initial data for the actual equation. Very close to curve. And the particular, of course, when we say curve is a two-parameter family matrix, so it's very close to a member of the curve arm. So this data is very close to some member of the curve family with parameters, I'll call them AI and MI. And moreover, I am going to assume that some extreme. But this is already clear in some sense by drawing. So the statement of the conjecture is the following. Solve the action equations. Then the development of spacetime, it shares certain qualitative properties of curve. Most importantly, there is still a complete future nullability. So of course there's two of them, I think, but I'm really only going to talk about, without also generality, one of these ends. So it has a complete future nullability. Moreover, the past of this future nullability will not be the whole space-time. This you can already infer from Penrose. Not of course the complete future nullability, but And the final statement is the following. As you approach this point, which of course the closest time I can get it, yes, but in the sense of these diagrams, as you approach this point, this solution is asymptotic to another member of the curve boundary. So, the member with final parameters, let's call it A sub x and M sub x, which will be near these parameters. So, this is the nonlinear stability conjunction of for the curve boundary. So let me make a few comments about this. So first of all, this kind of statement should be compared with the only context in the world of general relativity where we have a statement like this. That's to say, for perturbation of the process. So the celebrated theorem of Dimitris and such kind of you ask the analogous question for initial data which are here at the trivial initial data, then the evolution of such data is just complete and in some sense approaches from constant space as characterized. So the asymptotic stability of constant space. So in some sense this is the analogous question for the curve boundary, but there are some obvious even for the statement, additional features. So, what are some of these features? Well, feature 1 is the curve boundary is a boundary. There's only one enclosed space, but the curve boundary is a boundary. So, in particular, you don't know a priori which number of the boundary you're going to apply. So, one feature is in particular, you may think that you are perturbing, let's say, Schwarzschild. So your AI may be 0. You are not going to approach Schwarzschild. So in particular, there's no simpler stability of Schwarzschild. I mean, you could assume that AI is very small and hope that that's simplification, but you always have to think about that. There's no. And of course, another important difficulty of this problem, which is clear from the statement, is that stability really is this region here, in some sense, which is looking more and more like curve as you restrict closer and closer to this point. And in fact, if you believe certain other conjectures in the subject, for instance, something known as local filtering, then if you look at the curve, let's say, inside the black hole, and you approach this boundary, then the solution should be unstable. So, somehow, the region of stability is not the whole spacetime, it's a subset. And the subset, how is it characterized? It's characterized as the past. But of course, future non-infinity is not given to us, it's not a structure that you have to construct. So, all these issues. So let me actually make another point, which in some sense is already understood well, perspective of stability because of space. You might say that, well, maybe one is being too ambitious, maybe in some sense. Why is it that I want to know that you're approaching the curve boundary? Would it be good if I could just tell you, well, this panel diagram is in some sense stable. I have a complete functional infinity with nice smooth event horizon, but I don't quite know that I'm approaching the curve boundary. Maybe I oscillate, maybe who knows. What if I could just show how? That would be a start. But you can know this dipole theorems, it's either all or nothing, because everything comes as a package. So if you don't know how to identify what you are approaching, then you cannot show stability. And the reason is that the mechanism for stability, the only mechanism that we know that gives you stability is dispersion. So you have to know what you are approaching and what dispersion is. And if you cannot capture that quantitatively, then you cannot say. So that's what we would like to see. What result will I talk to you about today? Well, what I'll talk to you about today is this construction of dynamical black holes from the sky. And the statement of the theorem is simply the following. Well, instead of doing what we conventionally, that's to say, looking at initial delta, which is near the current family, and solving forward in time the action equations, and hoping that we can show that indeed the spacetime looks like this, and the solution is approaching curve in every direction as you approach this form. We're going to do the following. We're going to say, well, let's start at the event horizon. And on our infinity. So we start on the event horizon of infinity. And I'm going to prescribe data for the action quantum equation on the event horizon. Well, that's pretty standard, of course, the null type surface. You know what partition is. And data on now infinity will not consist of asymptotic constant data. So I'm going to prescribe here the data. And I'm going to prescribe the data in such a way so that the solution is approaching the curve found only by percentages. So it's approaching a particular number of the curve found with parameters A and M. And actually, I'm even going to allow the extreme ones. So the statement is the following. If you do this, you can solve backwards. You can solve backwards. That's to say, you can find the Cauchy hypersurface in this form. So you can go all the way to the Cauchy hypersurface. And now this will be a black hole spacetime with a complete future of infinity bounded by an event horizon, which in some quantitative way looks like sort of the black hole spacetimes that we think will always arise in sort of arbitrary terms. So now let me warn you already that we will see that there is something slightly unsatisfactory about the nature of this initial data. But I will also try to tell you that that unsatisfactory fact is in some sense necessary to correlations. But so this is the theory. And a particular corollary is the following. So in particular there exist black hole spacetimes which are not exactly curved. So there exist dynamical black hole spacetimes which are not curved. Where by black hole spacetime I just mean a spacetime that has complete functional infinity, but whose past is bounded by an event horizon as such as say complete functional infinity, its path is not a whole space. So even this statement. So this is good thought. Let me. I gave already a warning. Let me let you warning. So, remark one is that the concept, from the point of view of function counting, something you should never do. In any case, do it just for the second. From the point of view of function counting, these solutions are parameterized by quote complete specification of the initial value. That is to say, from the point of view of function counting, these solutions are quote generic. You are prescribing as much data as you can on the event horizon, and these are completely arbitrary functions. You are prescribing as much data as you can in a sense on functional infinity, for every such description, you have a space. So, in the sense of function counting, the class of spacetimes is very, very large. So, these are exactly the type of arguments that in the context of there used to be a conjunction consumption known as PKL, and this is the type of arguments that tell you there's a generic, this generic class. So by function counting, no, this should be almost in. But now here's the secret about the statement which I hinted so far. We will require something very specific, however, about the behavior of what the free data, the dynamic part of the data, on the temporalized and on the linear. And that very specific thing that we require is that this sort of the dynamic part, the wave part of the data, if you will, it decays exponentially along the temporalized and along the future. So we will require. On the other hand, even though we don't know how to solve this problem from the linear problem, which I'll talk about, we know that we expect generic solutions. If I look at the generic perturbation of initial data and solve forward, we expect that those fields will decay slow. They will not decay exponentially. They will decay polynomially. So, we actually know a priori that these spacetimes that we construct do not see the generic solution of the forward problem in the correct sense. Nonetheless, my claim is that if you want a statement of this type, a statement where you just prescribe data and you sometimes class of data is determined by simply a decay assumption, and you want to be able to solve backwards, this assumption of exponential decay is necessary. And I will tell you why that path is not feature. So now let me go on to tell you why the stability problem is hard, and then why this problem. So in some sense, the difficulties of the stability problem, they enter as three levels. So in some sense, a much more easy problem than the stability problem in the sense that I told you is the following. Fix curve, fix the bottom, and look at, but not the linearization of the actual equation, which is complicated, but just look at the scalar wave on that fixed bottom. You can think of the scalar wave equation as a poor man's linearization, where you forget about the tensorial. So, if you cannot understand everything about that equation, on fixed curve bottom, then certainly you're not going to do this problem. So already in that problem, many characteristic difficulties, they already occur. Well, the difficulty is that occur when you try to move from this formal linearization to the actual linearization. So there are difficulties which are sometimes not pure wave equation difficulties. They have to do with the tensorial problem. And finally, well, that's all linear on the fixed background. The projection is a problem projection. And there are problems obviously arise when we try to move from the linear problem to the non-projection. So in fact, let me go through these sort of three levels of difficulties one by one, tell you what they are, what is the status. So the first is the poor boundary optimization. So this difficulty is something that, of course, this problem that say that wave equation of fortune and currents is something that obviously has been a lot of literature on this problem, going back to Reggie Wheeler, and in some sense, I couldn't begin to list all the lots of literature. Reggie Wheeler, Arthur, Rice, etc. But from known classically until 5 or 6 years ago. Although many important properties of curve were uncovered, which sometimes are related to the behavior of waves, you will be surprised perhaps to learn that the status of that problem, wave equation on curve, was very clear. So for this curve, the only type of statement that was really understood was why on Portugal, in particular, solutions of this equation, if I start the initial data on Portugal, start the initial data of the wave equation, evolve, why solutions remain bound. This was the only thing that was really known. And this only in Portugal. So, it was not understand why and how to solve these details in Portugal. And in the case of curve, you don't understand whether you start initial data of the linear scale wave equation, why the solution not wrong. So none of this was understood. So, so this is the problem that the last 5 years has been solved by various people listed here. And it has been resolved in the full sub-extremal case. And to the extent that it's true, in the extremal case, that I will come to talk about that also. And of course, this type of problem you can also discuss in the case of what you want to be constant, or positive, negative. The negative case is even more interesting because you have to even define what you mean by evolution. In the case of negative, you want to be constant. Manifestly, you say that it's not going to have a role if there's a kind of boundary of infinity, you have to understand how to deal with that. That's something that has been understood on wholesale. Okay, so that's sometimes what, to summarize what's known about this problem, is one understands for this linear scalar problem exactly, quantitatively speaking, given initial data from the wave equation, solutions indeed disperse. They disperse some inverse polynomial rate and capture one. That's the same. So I don't want to give you the precise statement. I just want to say a word about the phenomena that, in some sense, the phenomena associated with curve that you have to understand to prove the precise statement. So, and in some sense, these are in part phenomena that you all know about. The first phenomenon is the so-called branch effect, discussed before. The second phenomenon is, of course, the phenomenon superrated, phenomenon of curve. And the third phenomenon is the phenomenon of drought. Now, this is slightly less familiar, which I'll very talks that mentioned this. And it's not something which I can promote to an additional difficulty is the fact that as you go towards the extreme of limit, then these phenomena are actually strongly coupled in a way that is not understood. And to drive this point home, it's because of the strong coupling that at extremality, it's no longer true that waves disperse in the same way that they disperse in the sub-extreme case. In fact, there's a remarkable recent development in spacetimes, and the result says that if you look at the derivative solution of the wave equation in transversal to the transversal direction of the horizon, translation invariant transversal direction of the horizon, and this derivative does not detect in the extremal case. So in the sub-extremal case, all derivatives detect, higher derivative. Take the first derivative, it won't detect. You take the second derivative in this direction, then for generic solution, it goes up. So the extremal case is unstable on horizon. We'll see. Okay, so let me tell you a little bit about it. I guess I should add, there's also this question about how to understand behavior here about infinity, but this difficulty was resolved when this problem was resolved in the process. So the redshift well, we all know about the redshift. Typically, so from the perspective of geometric optics, you have two observers A and B. I like to say as follows, that typically you said A to cross the horizon and B typically does not cross the horizon. But I prefer actually to have both A and B cross the horizon. But B cross the horizon at an advanced time which is later than A. And if you look at horizon crossing patterns, now there's a redshift factor which has to do with the difference in advanced time of horizon crossing. So this is the local redshift as we recognize. So this redshift depends on the positivity of the surface. So this is something very general that only sees now, so all this is stability mechanism. This is important. If you cannot understand this quantity, you will never understand how waves behave on black hole. This is good. Now, what happens in the extremal case? Well, the extremal case, this motion redshift at the horizon. Well, exactly because surface gravity is zero. This is the challenge. So that's one of the reasons why. So that's one statement. The other issue is supernatant, but for the sake of time, we'll say much. Everyone knows that, well, in Schwarzschild things are already sort of bad. In Schwarzschild, we have our favorite vector field d by dt, basically kind of like when you're far away. Well, the only issue is that on the horizon, d by dt is null. And of course, what that means is you have a conserved energy by Müller's theorem. You have a conserved energy. But that energy at the horizon is still non-negative definite, but it's general. So we don't understand everything at the horizon on the basis of conserved energy. In fact, this is why we need to understand the measure. Now, the curve, of course, this vector field, which was safely kind of far away, and now on the horizon is fortunate, well now, of course, it's going on this so-called ergo region where it's space-like. So, a priori, the conservation of this vector field is nothing. Okay? So, you can radiate more energy to non-infinity than you have initially. If you do, this is exactly supermatrix. So, even the question of why waves remain constant is completely open, a priori. And one thing you have to understand is what is that quantity? What is that quantifies? How much more energy can you radiate to infinity than you have initially? What is the notion of energy that, in some sense, is the correct notion of energy that tells you if that is final, I only radiate 10 times more to infinity, but that's it. You have to discover this notion. It's not what it is. And that's radiance. And dropping is from already from Schwarzschild. We know that the R equals 3 amps. There are non-geodesics on this kind of hypersurface that stay on R equals 3 amps. They don't go to the horizon, they don't go to the infinity. And it's very general as well. That tells you, as already the quantity classical obstacle, that tells you that you have one such non-geodesic. Now, the nature of any type of dispersive state changes. In particular, it's no longer true, though you can expect that if I know that the energy here is, say, 1 initially, that there is some polynomial rate of decay that I can prove, all right, that says that, well, the energy here is less than equal to 1 initial energy times t to some negative power. Can never be true. False. And the reason is that somehow, once you have one such geodesic, you can contradict it. So the proper quantity that you have to understand in order to say that at a later time I have quantitative decay rate, the higher one. And this is interaction. Okay, so in any case, these difficulties as you approach extremality are strongly coupled, exactly because the ergo region as A approaches M, begins to coincide with the region where you have track function. So at first that looks very, very bad, but it turns out that you actually have a curve. That's what allows everything to sit straight. Alright, so if you try it too, let me be quicker now. So what are the difficulties that arise at the level of linearized gravity? Of course, if you linearize around the trivial solution, then the poor amount of linearization is the correct linearization. So in harmonic ordinals, for instance, just take that naive approach and linearize, that each metric component, each linearized metric component, will satisfy exactly the scalar rate. Well, of course, as you all know, when you linearize against the non-trivial solution, then there's sort of a structure. And, well, you really have to start thinking about how you're going to write this in order to see the correct structure. Then we sometimes just make the following general comments. So, in general, there is no obvious Lagrangian structure of synchronization. So, even in Schwarzschild, what's the mechanism that tells you that you have bounded this, let's say, away from the horizon? What is the envelope of this d by dt identity? Even this is not clear. Moreover, we know that the solution of the linearization, not all components can decay, because after all, the linearization is going to see the nearby curve solution. Now, since we don't have some sense of d by dt, then what is the mechanism that keeps bounded those components that don't decay? Again, clear. And of course, now if we go to the non-linear theory, what are the difficulties? Well, first of all, there are the difficulties that are huge and took 500-page book to solve, proof of stability in closed space. But by now, they're all packed. So those are the difficulties uncovered and resolved by the initiative. Finally, mainly that because the equations have quadratic nonlinearities and also quadratic nonlinearities and primitives and quantity linearity, then if you just want to solve for a very small neighborhood at this point, I just want to start here and solve a little bit. You need such a structure. You just write blindly the equation, say harmonic ordinals, you cannot do that. So you need special structure. And well, that special structure was exactly what was discovered and what allowed the resolution of stability in the closed space. But it requires introducing something very, very elaborate. So, in particular, certain gauge, which is related to an alpha variation, there are another sort of either a double alpha variation, alpha variation, or constant variation, and look very, very carefully at how various spin coefficients and vertical components with respect to the frame factor. So it's only by very, very carefully looking that you can see why the nonlinearities are better than they first were. But now, of course, in the context of black hole stability, you have to take all these distances and ask how do they interact now with the fact that not all components that can. How do they interact with all these other and finally, we know a priori from the statement that you have to identify these final parameters of the solution. Because if you don't know how to identify these final parameters, you're never going to be able to show decay. But how are you going to do that? And moreover, how are you going to find the center of mass? So, all this. Okay. So, very quickly now, I will tell you why discovery problem is much functions. So, and again, sometimes it's best to look at it from the perspective, again, of the poor mass problem, the linear gravity problem, and the full mass. So, at the level of the full mass problem, let me first tell you what nodes are. So, in the case of Schwarzschild, then there is a scalar theory for the wave equation by now classical. And essentially, it's motivated by the d by dt energy dynamic. So very easy to show that if I have finite d by dt energy solution initially, okay, t equals 0, and I solve the wave equation, then I can make sense of the d by dt flux on infinity and the d by dt flux on the matrix. So it's a model, which is a map. So it's initial data set in this sort of energy which is naturally associated with d by dt. So this set to set of fluxes on infinity, direct flux on the matrix. And one can show, and this is sort of in some sense a minor refinement of the statement that solutions decay from a electron rate. You can show that this map is an isomorphism. Let's say you can solve problems. So if I give you flux with respect to d by dt on the electrolyzer, and a flux with respect to d by dt on infinity, then there's somehow a unique finite d by dt energy solution that gives rise to these fluxes. But this sort of d by dt theory, even if you just keep the scalar wave equation, if you look at curve, this goes out the window. And the reason is that the finiteness of d by dt energy, alright, does not tell you that this energy is finite. In fact, there is no quantitative relation between d by dt energy and energy fluxes. So the forward map is not going to find the first thing. So what do you need to do? Well, you need to introduce an energy to define a forward map, which is not conserved, it's not associated to d by dt, it's associated to time-like vector to capital N. So this is the notion of energy, which if this energy is finite, then the flux is. That's the right notion of energy. And the reason that you can do that relies in part on the redshift. The reason that this energy is well behaved on the horizon has to do with the redshift. So that energy actually wants to exponentially decay on the horizon. There were no bugs. So that's the answer. But that's great for the forward problem. But now what does that mean? Suppose I want to solve backwards with respect to this energy. Suppose I look at some hypersurface like this and I want to solve backwards with respect to this energy. Then the redshift is now a blue shift. So you see the redshift effect is a blue shift. If you want to solve backwards with this energy, you see, you go back to that view. You like to go exactly. So it's fundamentally because of this reason that if you want to solve backwards, then you have to impose exponential. So I'm going to skip a lot because so let me just say that because of this, sometimes once you accept this difficulty, the scalar problem is almost a triviality. So the analog of the main theorem of the scalar equation is essentially a triviality. You do not need to understand anything now. Super radiance, trapping, nothing. So in the context of linear gravity, however, already there is one very important issue that immediately sticks out, which is the following. Remember, in linearized gravity, not everything decays. So now you're going to be solving backwards, and you have this solution. So you have to be able to write the equation in such a way so that the blue shift does not act on everything. Because you certainly don't want those things that are not decaying to start exponentially growing, then you would never be able to solve backwards. So already somehow at the linear level, you have to be very, very careful about construction, and particularly how to start very fast. So, and of course, in the non-linear context, well, I haven't really said much, so I don't know even tell you. So, this was a little one-slide summary of the proof, which this last independently already in 10 seconds, you will understand everything about the theorem, and also the technical details. done simply with the following conjecture. So, this conjecture hopefully will resolve part of the paradox. So, what did I tell you? I told you before, if you want to solve backwards, then it seems, because of this bullshit, that you are forced into imposing exponential descent. So first of all, what would happen if you didn't impose exponential? What would happen if I looked at the initial data here, which was decaying polynomial? What would happen if you try to solve backwards? Well, you would at first think that you can't even construct a space. So that would construction be the first thought on the basis. But of course, you're actually going to have a local structure. So I would be more optimistic and give you the following projection. If you look at generic polynomially decaying data at the event horizon and infinity, and you solve backwards, you can solve. So you can construct the space. There's a single structure. But the horizon will be singular. In fact, the horizon will be some sort of non-singular. So, this is the conjecture. There's even a relation between this so-called rotating problem space. So, now to resolve the paradox. So how is this consistent with the statement that, of course, the generic solution, which we certainly have a smooth horizon, has this polynomial decay? Well, it's consistent with the following sense. What's obviously going on is that if you look at the generic solution of the forward rule, there are some non-local correlations between the data at infinity and the data at the event horizon. And these non-local correlations will tell you that these data, they came from smooth initial data. So that fact is hidden in the non-local correlation. If you perturb the data at infinity and on the event horizon, in the class of sort of data which was decaying polynomially, and then try to solve backwards, you have interest. So it's not the decay rate at the event horizon and on infinity that tells you that it came from a smooth solution. It's something else, something different. So with that note, I have to leave it. Just very much.
Are there any questions defining the dynamics of the parameters A and U, A and M?
Well,
can you derive any?
Not so simple. I mean, there is a sense in which you can understand. Well, certainly, depending on. No, it's not even a well-defined notion. What mean as glorified these parameters, let's say, intermediate. So, with, of course, M, you can sort of think of M as being Bondi mass, and then, well, for the Bondi mass, we know from the stability of Minkowski space that there is a way of defining asymptotic evolution on infinity, and certainly, if the conjecture is true, then the final M parameter will be the sort of limit of this mass in the right rank. Now, with the notion of angular momentum, it's more subtle. There isn't a completely general good definition of angular momentum on infinity. So, in some sense, it's a priori, it's not yet possible to even entertain per se the question. But I have no doubt that the solution of this conjecture will shed light on that issue, and so in particular, you will have to sometimes understand the dynamics of some asymptotic object at infinity, which will, in particular, asymptote to X. Right? But this is not completely understood the right framework.
Other questions? No, we can bring up some